In this video, we're going to look at one of many proofs for the Pythagorean theorem. So before we do that, though, we have to remember some vocab and remember what the Pythagorean theorem is. So whenever you have a right triangle, you have a hypotenuse and two legs. So the hypotenuse is always going to be the side across from the right angle. So it's the longest side. So let's label that. So we go to the right angle, go across from it. That's the hypotenuse. And then the legs are just the other two sides. So the legs, it doesn't matter if they're congruent or not, we just call them the legs. So when we go to use the Pythagorean theorem, what it says is that the sum of the squares of the legs is equal to the square of the hypotenuse. So that's our a squared plus b squared equals c squared. So I'm just going to write that nice and big here. And when we look at that, remember the legs A and B, you can interchange them. It doesn't make a difference, but the longest side always has to be the hypotenuse. So C always has to be the hypotenuse. And the most common use of the Pythagorean theorem is to find the missing side of a right triangle. So I'm going to just add that here. Most commonly used for finding the missing side of a right triangle. And one thing to make note of is the Pythagorean theorem only works when you have right triangles because you have to have that hypotenuse. And some of you use Pythagorean theorem instead of distance formula. So again, you're using it to find a missing side length. And then another use that's not as common, but it's to classify the type of triangle. And you'll see this in the check your understanding. But there's different ways that you can use the Pythagorean theorem to help classify what type of triangle you have. But for right now, just recall that it's used to find a missing side, most common use. So what I want to do is I want to show you one proof of the theorem. There are numerous proofs. If you just Google Pythagorean theorem proof, you will find so many different proofs. I want to show you one, and I like this one because it's visual, so it makes sense to me. So hopefully it'll also make sense to you. So what happens for this first proof is you start with a picture that looks something similar to this. So basically you have this larger square with sides a plus b. So this entire side would be represented with a plus b. Same thing with this side. So that's the side length of the square. And then you have these four corner pieces that are triangles that have sides A and B and C as the hypotenuse. Now, since it says that we're given a square, I really know that all of these are right angles. So I'm going to go ahead and mark those as right angles. And the inside piece is also going to be a square. So there's really right angles there as well. So what ends up happening is you have these four triangles and you have another square all inside this larger square with side lengths of A plus B. So in order to do this proof, there's two steps. You first are going to rewrite the area. So here's our two steps. We're going to rewrite the area of this square using its side lengths. So area formula for a square is base times height, length times width, or side times side. So if I take and I rewrite the area of this larger square, so this entire square, it's base times height, so it's going to be a plus b times a plus b. And then I want to actually go through and simplify this. So when we simplify this, you can FOIL. Some of you might remember from algebra doing the box or the grid to help multiply. I like to use that because, again, it's visual. So you're either foiling or I set up a grid, so it's a 2 by 2. So I multiply, I get a squared. I multiply these, I get ab. Multiply here, I get a times b, and then b times b is going to be b squared. My like terms occur in the diagonal, so it's going to be a squared plus 2ab plus b squared. So that's my result. So I'm going to just rewrite it over here. So a squared plus 2ab plus b squared. So that's the area the area of this entire square using the side lengths. Now the next step is to find the area of this square but using more of a dissection. So meaning using all of the little parts. So meaning I have four right triangles. So you have these right triangles. So those 4 right triangles, the areas of those 4 right triangles plus the area of this square right here would represent the entire areas, or the entire square's area. So what that means is if I want to represent that, the area is going to be the area of the small square plus 4 times the area of all those little triangles. So what that translates to is the area of this small square here is going to be C times C. So C times C plus the area of the 4 triangles. So I'm going to do 4 times. Now to find the area of one of these triangles, if you remember area of a triangle, so off to the side here, area of a triangle is base times height over 2. So that means the area of the triangle, the base is A, the height is B, or vice versa, the base is B and the height is A, doesn't really matter, but I have A times B and then over 2. So that's the area of one triangle, so I'm going to plug that in here. So A times B over 2. And right here represents the area of this larger square. So there's 4 pink triangles and 1 square that has side lengths of C. So that's what I've done here. So now let me just kind of simplify this a little bit. So it'll be A equals, so C times C is C squared. These are going to cancel. 4 divided by 2 will be 2. So it'll be plus 2A. So what I've done is I found the area of the square using a dissection method, which means all the little parts. And I found the area of a square using its side length and then plugging into the formula. So these two things have to be equal to each other because they belong to the same square. These are both legit methods for finding the area of the square, and we're using the same square, so the areas have to be the same. So now for this last step, what I can do is I can set the two equations equal to each other. So set the 2 areas equal. So set the 2 equations equal and solve for C. So this is really my third step. So what I'm going to do, I'm going to take these 2 pieces, they have to be equal. So A squared plus 2AB plus B squared equals C squared plus 2AB. I'm just looking up here. I don't know if I wrote it and it disappeared or I never wrote it. There should be a B up there. 2AB, because right here, 2 times AB. So I might just, I don't know if it disappeared on me or if I didn't write it. But make sure you have that. So 2AB. So then what happens is hopefully now you see there's a common piece between both of these. It says to solve for C squared, but really I am going to be solving for C squared, but really you have a common piece on both sides, so they cancel each other out. So now what I can do is if I just subtract the 2AB from both sides, those are gone, and I'm left with something you know, A squared plus B squared equals C squared. So we've just verified that the Pythagorean theorem is true when you have a picture like this. So when you're given a picture, we've just verified that A squared plus B squared will equal C squared. So there's one of many proofs of the Pythagorean theorem. So now what I want you to do is I want you to try the check your understanding page. It's not about proving, but it's about using the Pythagorean theorem. So using it to find missing side lengths of right triangles and also using it to classify. And there's a little description to help you with that on the next page. So go ahead and try those, and we will talk about those tomorrow.